Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. I am pretty pumped about today's video. Today we're talking about triple integrals. Triple integrals are very exciting because I'm getting a little bored of double integrals. Double integrals are not enough integral. I need at least 50% more integral per integral. So we're going to triples. It's the only way. Triple integrals are, in some ways, a lot like double integrals. So, if you're pretty comfortable with double integrals, this isn't going to be a huge leap for you. But they're different enough that I should spend a video or two talking about them and going over the differences. The thing that is the least different between double and triple integrals is the process of finding the antiderivatives and evaluating them to get like your actual result. So like once you have a triple integral in front of you, evaluating that triple integral is very much like evaluating a double integral. It's just about 50% longer. So that's going to be the easy part. So this first example we're going to do, I'm going to kind of go through that process because that process is the most straightforward part. But while we're going through it, I'm also going to talk about like what's happening, what these pieces mean, what the difference in interpretation and meaning is between the triple integral we're doing and the double integrals we've done before. So I'm going to throw this integral up on the board. I think it's a pretty good one to start with. We're going to go from z equals 2 to z equals 3. That's a big, exciting new thing already. We've got z's involved. It's not just x's and y's anymore. Now we're doing x's and y's and z's. On the other axis, we're going to go from 0 to pi over 2. These will be our y values. On our third axis, we're going to go from 0 to the natural log of 4. This will be our x values. And we're going to integrate e to the x cosine y z squared dx dy dz. So, as I said, the actual process of finding antiderivatives, evaluating them at these numbers, simplifying, doing the next antiderivative, the process of transforming this into an answer using all the calculus we know, that process hasn't changed from double integrals. It's pretty much exactly the same. You start from the inside out. We're going to do this dx integral first. Then we're going to plug in our bounds for x. And after you've plugged in your bounds for x, that variable should never appear again. Once you integrate on x, the only thing you have left are y's and z's. And then we'll integrate on y, and we'll plug in those bounds. And once you have finished that, there's no more y's. Y is gone. It's done. We're game over on y. And then lastly, you'll integrate on z's. And for z's, you have to plug in constants because we're not bringing x's or y's back into this. And then at the end of everything, you should have a number. So some of these things, I mean, aside from the actual integration techniques that haven't changed since Calc 2, and the fact that we're going to pretend, like when we integrate on x, we pretend that y and z are constants. So we're going to treat these pieces like coefficients. That hasn't changed from double integrals. The other thing that definitely hasn't changed from double integrals is we can put functions here. Your innermost integral, in our case this dx integral, this can be, as for the bounds I mean, you can have a function of y and z. Your innermost integral the bounds can be a function of the other two variables. And then the middle integral can have bounds that are a function of the last variable. and your last integral always has constants. That is not the case in our integral that we have here. The integral we have here is nothing but constants. X is going from 0 to the natural log of 4, y is going from 0 to pi over 2, z is going from 2 to 3. All of these things are just very tame, regular constants. They're honestly pretty boring. And that's another thing that hasn't changed from double integrals, is that when you use constants, you get rectangular regions. So we definitely need to talk about these regions a little bit as well. In terms of the bounds, x going from 0 to natural log of 4 is two just vertical flat functions. Y going from 0 to pi over 2 is two vertical flat functions on this other axis. And z going from 2 to 3 is two vertical flat planes on this axis. And when you take space and you cut it like this, and like this, and like this, you end up with a box, a rectangular prism. So that's still true from double integrals. When we use nothing but constants all the time, you get a box, a rectangular prism. This is good to keep in mind because there will be many tests and quizzes in which I will ask you to integrate a region that is not a box. And one of the most common mistakes students make is they will use all constants for the bounds. And that, as far as mistakes go, like there's certain mistakes that I can understand pretty easily. That mistake has always blown my mind, because if it's all constants, you have a box. If you don't have a box, they shouldn't be constants. Just use functions for some of them. Get the curvy shapes or the slanty bits. The curvy bits and slanty bits, they always come from using functions as bounds in the inner or middle integrals. If it's all constants, you have a box. If you don't want a box, you can't use all constants. Right, so let's talk more about the idea of a box. If these constant bounds create a large box space somewhere that we want something of, then we also need to talk about what this represents. In double integrals, we had dx dy, and the book referred to that as dA because this was a tiny chunk of area. And floating above our tiny chunk of area, our dx dy was a little box, little two-dimensional, tiny little infinitesimal square. And above this square we had this pillar of space that went up to the height. This was our area, and we were always integrating f of x, y. This was our height. And when we multiplied this tiny little chunk of area by our height, we got a volume. And so when we did all these double integrals, we were finding volumes. Triple integrals are going to be a little different sometimes. So the most basic sort of, I guess not the most basic, the most mundane, we'll go with. The most mundane interpretation of a triple integral is there is no interpretation. Stuff like this is probably just weird made-up nonsense for a mathematical exercise that doesn't represent anything in the physical world. It's just practice for us to do the math process. This doesn't mean anything. When these triple integrals mean something, they will usually mean one of two things. This piece by itself is a piece of volume. In the same way that dx dy is a chunk of area, dx dy dz, got your tiny little box and your tiny little height, that's all three dimensions. When you multiply those things together, you have a tiny little box of volume. So this is already a volume. What are we multiplying a volume by inside this integral? we're not multiplying an area by a height to get a volume and then adding up all the volumes. We already have volume. So what's all this? There's two things happening here. Most of the time, there's not going to be an all of this. Most of the time, you're going to be integrating the function 1. You'll see things like this a lot. Integral, 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 dx, dy, dz. There's going to be like an absent function. So if this is already a volume, you don't have to multiply the volume by anything to get a volume. We have volume, you multiply that by 1 or nothing if you don't want to deal with writing a 1 there, and you integrate over your bounds and you get your volume, and that's great. So what does it mean when there is a function there? Sometimes, again, just mathematical practice, doesn't mean anything. When it means something, it is because this is a density function. So this will give us a tiny, tiny little piece of volume floating somewhere in 3 space. Maybe x is 1 and y is also 1 and z is 2.5. That is a point, one of the infinitely many points that exists in this box of space defined by these bounds. If you evaluate this function at those points, it'll tell you the density of that particular particle of mass. This is for 3D solids that have variable density. So it's not like we have a brick where it's the same density throughout. Maybe this is some weird fluid that is more dense in some places than it is in others. Or maybe it's a chamber where air pressure is varying wildly. Or maybe this represents the temperatures. No, it wouldn't represent the temperature. We don't add temperatures together. Density is usually what it goes with. If you have a space, a solid something, where the density is changing throughout this shape, and you want the total mass of that object, then you need to calculate the density at each of the infinitely many points in that object. You multiply the density by the volume to get a mass, and you integrate over the bounds of your object to get a total mass of the whole thing. So your density function times your tiny, tiny, tiny little infinitesimal chunk of volume will give you a tiny, tiny, tiny infinitesimal chunk of mass at that point. The triple integral will add up all those masses to give you the total mass of your thing. That was a lot of explanation for something that's honestly not going to happen much. Most of the time we're going to be integrating volumes, and we're just integrating the function 1, and whichever first integral you do here is effortless, because the integral of 1 dx is x, and you're already done with that first step. Sometimes we're just going to be integrating functions for the sake of integrating functions for mathematical practice, and it doesn't mean anything. But sometimes we're going to be integrating density functions to find the total mass of an object. That is the what does this mean sales pitch. So let's just get started working on it, and we'll see what happens. The first integral is with respect to x. Cosine y and z squared are effectively constants for this integral, and since they're all multiplied together, that makes them coefficients, and we can pretty safely ignore them. Coefficients are safe. So we're going from z equals 2 to z equals 3. Y is still going from 0 to pi over 2. The integral of e to the x times coefficients is e to the x times those coefficients. Cosine y, z squared. We're evaluating that at 0 and natural log 4. And the dy and the dz stay around. Here's an interesting observation. Don't change the order of these. Like for these first couple steps, we're just going to leave the z and the y integrals alone. like they have nothing to do with these first few steps, make sure that the order doesn't switch around. Because the book doesn't do this z equals y equals business. The book just puts numbers here and expects you to recognize that the numbers go with these d's in this order. So if you accidentally switch the dz and the dy halfway through this, it's going to get real messy real fast. So dy dz is the order. Going to make sure that I maintain that. E raised to the natural log of 4 is 4. E raised to the 0 is 1. 4 of these things minus 1 of these things is 3 of those things. So z is 2, z is 3, y is 0, y is pi over 2. After you evaluate this, you get 4 of those minus 1 of those is 3 of these. 3 cosine y z squared dy dz. Here's another important thing to remember to not make mistakes on. A lot of times when you evaluate something at 0, it just goes away. It's zeros and everything is multiplied by 0, so you end up, if the 0's on the bottom, a lot of times that just means you can skip the part where you subtract the bottom piece, because you're subtracting 0, but not always. Do not be hasty with that evaluation. Take your time on that one. Now we're evaluating the antiderivative of cosine y times coefficients dy, so that'll just be z still going from 3 to 2. The antiderivative of cosine y is 3 sine y z squared. 3 and the z squared don't change, those are just coefficients. We're evaluating this at 0 and pi over 2. dz is hanging out on the back end. So evaluating at pi over 2 gives us 1. Evaluating at 0 gives us 0. So this is 3 z squared minus 0. So now we have the integral from z equals 2 to z equals 3 of 3z squared dz, which is of course z. I keep on trying to write x's when I say z's. This integral is z cubed, evaluated at 2 and 3, which is 27 minus 8, which is 19. That seems like enough of an introduction for our first video. This is part 1. Stay tuned for part 2. There's still lots to talk about.